Okay, so hi everyone. Today is actually the first, I think, really interesting lecture because we are going to do non-trivial stuff. So far, we defined non-trivial definitions, but we didn't really do anything non-trivial. And we are definitely going to prove Riemann's theorem, which is a big theorem in this field. It's half of a very big theorem, Riemann-Roch, which we'll see next time. And we are going to define the genus. The definition of the genus of a function field is kind of only makes sense once you see Riemann's theorem. And we are maybe, hopefully, also going to talk about Gopa codes and see at what extent. But we have some preliminary work still. And last time we started to prove lemma 10. And lemma 10, if you remember, said that if you take any finite set of prime divisors, and you take A and B pseudo divisors, such that A is at most B, namely every prime divisor here appear with less multiplicity than here, or equal, then the dimension of the Riemann, essentially Riemann-Roch space, truncated the version of the Riemann-Roch space of B compared to that of A, and indeed, because of this is a subspace of that, so it makes sense to write this thing, is exactly equal to the difference between the corresponding degrees. Okay, so that's what we started to prove. Okay. And actually, so we started to prove this, and the first thing we did, using essentially the Ford isomorphism theorem, we said that it is enough to consider the case where B is just one prime larger than A. Right? Because then you can kind of repeat it, S is finite, everything's okay. And for that, what you want to prove is that, so let me kind of spell it out. So now this is B. And what you want to prove is that you want to prove this theorem, but the difference between the degrees is just what? The degree of P, right? Because the only thing that's here and not here is P with multiplicity 1. So the difference here is, in this particular case, is the degree of P, so that's what we want to prove. Okay, so let's continue with this proof. Any questions about what we want to prove, or context, or anything? Everything's okay? Okay. So just a sum of prime divisors that could be infinitely supported, whereas the divisor, it has to be finitely supported. But when you restrict to a finite S, you essentially get a divisor. It's kind of weird. We are going to remove this truncation, and we're not going to see tilde beyond like 1.5 hours from now. So at the end of the day, we are going to work only with divisors, but we're not there yet. So I have to consider this more general thing. Now, I actually want to move things around here. I want to prove another claim, which is even easier than that. And that actually will be essentially almost trivial, or I don't know, let's see. So essentially, I want to take this to be 0. I want to have a 0 here and minus B here. Okay, so I kind of want to remove A. And in order to do that, I'm going to use a trick which will seem weird initially. The entire lecture today is going to seem weird because these are like really thought of proofs. So it's not the first proof that you'll think of. It's not the second proof that you'll think of. It's a more succinct, less insightful proof that you'll see ever. And this one is just a preliminary for what's coming next. So by the weak approximation theorem, right? Do you remember the weak approximation theorem? So I'll remind you, but I mean, in this example, you can find an X. I'm going to use this X kind of to shift things around. So you can find an element, a function, such that for every Q in S, recall S is finite, so weak approximation theorem holds. So for every Q in S, I'm going to demand, I want this element that I want to use, I want to have a valuation, Q valuation of that element to be exactly what's written at the kind of coefficient of A plus P at Q. Right, so this is another VQ than that, right? This is the VQ of functions, this is VQ of divisors or pseudo divisors or whatever. This just says, take the coefficient of Q in this divisor, it's a number, and I want x to have VQ of that to be that number. Okay? So another way of writing that, instead of saying for every Q in S, the evaluation agrees, I can just write it like succinctly in with divisors. I can just write it like that. Right, the principal divisor of x truncated to S should be, or I mean, I found an x such that it equals to the truncated version of A plus B. Just because that's the definition of equality and truncation. Now, if you remember, we had something that's called claim 9, if you look at the notes, but don't worry, I can remind you, I'll remind you. So we had this claim that tells you that if you take a Riemann-Roch space, or even a truncated Riemann-Roch space, and you multiply it by x, and recall x is a linear operation. So it takes this vector space to another vector space, and that vector space is what? If you remember? Exactly. I'm going to shift A, this is like A plus P by X with a minus. What happened there? But what is A plus P minus X when you truncate it to S? Because of that? 0, right? Because they agree all the time. So that's the 0 divisor restricted to S. Technically, I should write a restriction to S here, but that's the same. So you can just write it like this. So you see, I promised you that I'm going to take A plus P to be 0, and that's what I'm doing. And what can you say about X times the thing that appears here? Right, so that's, yeah, exactly. So that's this thing, because of the same argument. And that's L of what? P or maybe minus, yeah, just because, yeah. Otherwise, it would be bigger or something. Yeah. Good, and as you said, they are isomorphic. So I mean, this is isomorphic to that. This is isomorphic to that. So if I want to prove, if I care about dimensions of the quotients, I can replace both of them by these two, because they are isomorphic. So the ratio of dimensions will stay the same. So let me just squeeze it here. So it suffices to prove that the dimension of this Riemann-Roch space, which looks like weird a little bit, is the big P. Right? Okay, so let's prove that, unless there are any questions. All good? So this is like a cosmetic application of the weak approximation theorem. You don't really have to do it, right? It's just more for convenience, really. You kind of feel it. Usually, I mean, in what will come later in the course, we'll use it more heavily, but still, it's a nice kind of a nice thing to have. It's essentially what happens is that you had a class of functions, and you divided all of them by x. That's really kind of what happened in terms of like functions and not divisors. And then, you look at another class of function, which is nice. You made sure that poles and zeros of that agrees with that, so they kind of canceled out in a sense. So that's kind of what's happening here. If you look at the functions themselves, but we don't look at them. Okay, so what can we say about L0S? So L0S, because P is in S, is certainly, I mean, this Riemann-Roch space, this truncation, or the Riemann-Roch space of this truncation will only increase if I remove some of the element of S. Right? Because elements of S are restrictions. For every element in S, I want something to happen. Here I'm only leaving P. P is in S. So I'm overlooking everyone else. So there are less constraints here, so that this is a subset of, or subspace of that. And what can you tell me about this? If you look at it for a second, what is it? It's like an old friend. It's not from the board. P is in S. That's why it's true. Yeah, right. Otherwise, it's not true. Sorry? So these are all functions, right? That have no poles at P, and no requirement otherwise. So we have a name for that. Exactly, OP evaluation name. That's a way of writing that. So like L0 of P comma Q is the intersection of OP and OQ. Right? But L of OP is just this thing. Just if you think about it, all functions for which the valuation at P is at least 0. So that's exactly this. And no other requirements. Because S is only P. Good, so we have that. And now let's denote the residue field. Usually we denoted the residue field by F bar, but now we have a P and I want to address it. So F sub P is this residue field that we always have. And what we are going to show, so we'll show, in order to prove the equality of degrees there, that restricting the projection map, the usual projection map, like the evaluation essentially, by this projection map. When you take an element here and take it to its coset, that's an evaluation for us. We also have to take everything else to infinity, but just considering that. So if you consider the projection map, so we're going to show that restricting this to L0S, which we just proved is a subset of OP, so it's indeed a restriction. Namely, so just let me be more explicit, we are going to look at this map that takes x to x plus mp. Right? It's the same map, but restricted to this smaller domain. We are going to show it is onto, and with kernel, what do you think the kernel I want to have to be? I mean, I want to prove that. So I want to prove that, yeah, right. So it's this thing. I want to prove it's this thing. Uh, 0 minus 3. No, I was okay. Yeah. Right, because look, what's happening is this. Here you have, and that's our philosophy in the entire thing. Here you have structure, here you have a number. And you want to prove that they're equal. And you don't work with numbers, you work with structures. Like once you have vector spaces, there are isomorphism between them and stuff. You don't work with numbers. Numbers are not equal. You can't say anything about a number unless you know where it came from. So degP, we know what it is. It's exactly, the definition of the degree of P is exactly the degree extension of this over K. degP was defined to be, you look at the residue field, it contains K as a subfield, what's the degree extension? That was the definition. So if you want to understand degP, you have to kind of go to FP, unless you use some claim that before used that. But like if it's the first time you're doing it, you have to look at FP if you're close to the definitions. So that's why I kind of said denote FP, which might have looked weird initially. And okay, so I know that degP is FP over K and the index of FP over K. So if I want to prove that, I have no other choice essentially but looking at the isomorphism from here to FP and hope that it's onto and that's the kernel. That's what can you do? That's the only thing you can do. It's like the most greedy proof. Like ChatGPT can think the first step that you'll do, you have to do it. Even though initially it doesn't, it looks like smart or something. But okay. Maybe also let's fix this line a little bit. Yeah, so, right, so that's the goal now, to prove that projection map restricted to this is onto and has this kernel. So let's start with the onto, it's harder. Sorry, 22. Right. So, okay, I want to prove it's onto, so I'm going to take an element here. Take x in FP. And I want to prove it's onto under this map. But I know it's onto under this map. Right? I mean, this map is a projection, it's onto. You take x to x plus mp. which I called, sorry, maybe I should go it like that, just to think of it as an element in f hat or fp hat. So I know that there exists x, not where I want it to be, but here in OP, such that indeed, phi p of x, which is x plus mp, maybe it's better to write like that, is x. Right, there is an element from OP that goes to x hat, let's call it x, and we really want x to live here and when I'm done. But it doesn't have to live here. I need to fix it a little bit. It could have like holes outside and stuff like that. So I'm going to take this little x and build on it to construct another element, which I call y here, that does live here and also goes to x hat. Okay? Because it's not that any element, any pre-image is in L0S, right? This is a finite field in my mind. This is a huge field. Every element here has a huge number of pre-images. Not all of them are going to be here, but I'm going to fix it, to manipulate it so some version of it is going to live here. And for that, you need the weak approximation theorem. So by the weak approximation theorem, I mean, what's the problem? The problem that here, I have more requirements than here. Only finitely many, but I have more requirements. Here, I don't want to have functions with pole at P. Here, I don't want to have functions with pole at any element in S. So I just need to kind of make sure that that's the case. So by the weak approximation, I'm going to, I write it as there exists, but I'm going to find a y such that now I can list any finite number of constraints and that won't contradict each other, and then you're fine. So first of all, actually second of all, it should be first. I wrote it second here. Like pedagogically, it's not the same. So that's what I said before. I want this element to actually live here. I don't want it to have poles outside of P. And just by being here, it doesn't hold necessarily, right? Because this doesn't care about places other than P. So first of all, I'm going to make sure that the element does live here, at least for everything that's outside that is not P. And I don't want to just require that also for P. I want to find an element that also projects to X bar. So in a sense, I want an element that is close to X, that looks the same. So what I will require in addition is that VP of y minus x is strictly larger than 0. Strictly larger. I can put equalities and I'm still fine by the weak approximation. I can do that, but I just want strictly larger because that would immediately imply, just see that immediately implies that what can you say about phi of y minus x? Vp of y minus x? 0, exactly, because a function has valuation which is positive means that when you evaluate, you get a 0. So this means that Vp of y minus Vp of x equal to 0. So let me write it like that. Right, because it's a homomorphism. And that's x bar. And indeed, we found a y that goes to x bar. That's a good thing. We wanted that. And we just need to see that all of this, it does imply indeed that y sits here. And then we are done with the onto. Okay, so why does it sit here? So actually it sits here almost immediately. For every q in S that's not P, it satisfies the requirement. We just need to make sure, because I didn't write, I couldn't write this. I couldn't have written that because I can't put, in the weak approximation theorem, I can't put two constraints on the same P. They may contradict each other, generally speaking. So I didn't put that. I omitted P from here because P had a different role to play. But I claim that it just follows from these two that Vp of x is indeed larger or equal than 0. And do you see why? Right, exactly. So I can use the strict. So you can write it like that. That's equality. Just put it like that. No, I don't want that. Sorry. Yeah, I thought you wanted to add it here. Good. So maybe I should do this. That's better. And that's the minimum, at least the minimum between Vp of y minus x and Vp of x. by this triangle inequality, and then we are done, because this is actually larger than 0 even. I mean, I use the fact that it's close to x. This is larger than 0, and this is larger or equal than 0 because x is in OP. X is in OP means the VP of x is at least 0. Right, so that was actually a stronger statement, than what we needed, so. Good, and that's why it's onto. Questions? So let's just finish by proving the kernel is exactly what we want. That's kind of obvious by definition. So take an element in L0s, then phi of x is 0. I want to say if and only if x is in L minus ps. Right, but this is 0 by definition. If and only VP of x is what? Greater, actually. Right, greater. Right. Because this means this means that x has a 0 at p. So maybe it has 2 zeros. You can't see it from here, but it has at least 1 0. Okay, but x is here, namely at any prime divisor outside of p, like every divisor in S, sorry. It doesn't have a pole, and it actually has a 0 at p. So actually, what I can do using that and that, but that's given that this is equivalent, I can say that I can actually strengthen my understanding. I'm claiming that x is actually in here even. You see, being in here means x has no pole in any of these places. And this tells you additional information. I'm doing that direction, but you can do the other one. That gives you the extra information that not only x doesn't have a pole at p, it actually has a 0 there. So it actually puts x in this Riemann Roch space. Right? The minus is stronger. It says that for every element in S that's not p, you have zeros here. So it doesn't have a pole, but at p it is required to have a 0. Right? Because VP of x minus 1 should be at least 0. And we know that. I mean, actually, these two are equivalent given this. So that's proved that's what we wanted to prove. That the kernel is exactly this thing. Okay. Questions about the proof? It's a non-trivial proof, but it's going to be like that today. So we stopped with definitions, and now we're doing proofs. Really. Any questions?
What was the statement we?
Yeah, that's good. A good question. So yeah, I'll just write it down so that we'll have it here, because it was kind of a long time ago at this point. A week minus 2.5 hours or so. Think about it. So we proved that for every S finite, a subset of the places, and for every pseudo divisors A and B that have this, then the dimension of L BS over LAS is exactly the difference between the degrees. And actually, I forgot to say, last time you said, it's interesting because these are actually infinite dimensional vector spaces because S is finite. So you only have finitely many constraints. On the rest, you have like infinitely many choices. So each of them is infinite dimension K vector space, but they're close, they're the same infinity essentially. Their difference is this finite number. This was a good point. So that's the thing that we proved. It's just a technical claim that will be used. Let me give you another claim. So let's say kind of independent of that. So let's say you take a divisor now, so finitely supported, but it's negative. Negative means that this is the 0 divisor. So it means that every prime divisor here has a non-positive coefficient, and at least one has a negative coefficient. That you're strictly smaller than 0, 0, 0, 0, 0. So you can't be larger than that anywhere, so it's non-negative, non-positive, sorry. but it's strictly larger, smaller than 0. So at some point, maybe more, it must be negative. That's what this means. And if you remember, negatives are a requirement. So you kind of would expect that here you only have requirements. You give me no freedom whatsoever. Like there is no place here which is positive. You don't give me it is allowed to have this and that many poles. You only require zeros all the time. So what do you think will happen to the Riemann-Roch space? Like you require and require and require, and you don't give anything back. Trivial, exactly. Trivial is a good name to, like, I'm not sure what trivial is, right? But trivial is this. Like, trivial, really, as a vector space. Because it's a vector space. 0 is always there. 0 is fine. 0 valuations are always infinity. So everything, I mean, 0 is in every Riemann-Roch space. And what Itai is saying is that this is I mean, if you don't give me any freedom, then you are forced to be trivial. Right, for example, remember that we had this example that in the rational function field, that's the only function field we can currently analyze. This was all degree at most R polynomials. Right? So you allowed me R poles at infinity. A minus would require a 0. So this means only requirements, nothing there. It's fair, right? I mean, sorry, where? A equals 0? Or less than 0 means, no, it means that, I mean, at some places it could be, so an example of A could be like 0, 0, 0, and then a minus 3, and then 0, 0, 0. This is like an example. So this means that you are not allowed to have poles, and you are required to have zeros. So
less than or equal is not less than or equal taking every coordinate, it's less than, less than, like strongly less than
right.
coordinate, at least less than 1.
Exactly. So this is according to the order of divisor. So that means that, right, it's not in everywhere it has to be strictly smaller. There should be, this is an example. There should be enough, it is enough to have one place which is strictly smaller, and all of the rest can be equal. Right? It's not like a point-wise inequality. Good point. Because then your interpretation is the right one. Okay. So just to prove the claim, let's just remind you something that I think you will see today. And we said last time, we said that every x in f minus k, every element, every proper function, not a constant, has valuation, has a 0 and a pole, has v and v prime, such that v of x is larger than 0, and v prime of x is smaller than 0. Right? Every function has a 0 and a pole. You'll see it today, but let's take it that with us. So now let's see. So let's take x in LA. I want to prove there's nothing there. I want to prove x is 0. So what do I know? I know that for every p in P by definition, Vp of x, I should write plus Vp of a is at least 0, but I'll just move it around like that. That's the definition. And this number is at least 0. For some q, it's going to be actually strictly larger, but at the very least, this number is at least 0, because each of these numbers is at most 0. Right? It's like you can't have like a 1 in every place. So this number is at most 0, so this number is at least 0. I'm just using like the smaller equal now at this point. But that's that. So this means, so if you read it, what's written here? It means that x has no poles. Right? For every p and p, Vp of x is strictly or larger or equal than 0, no poles. No function has no poles unless it's in K. Right? So this means that x is in K. I want to prove that x is 0, but we just prove that x is in K. Because this just says x has, this is the interpretation, no poles, and that's impossible unless you're constant. It's actually equivalent to being constant, right? But now let's use the fact that there is a q which is negative that we didn't use. So, we also know that there exists a q in P such that vq of a is strictly smaller than 0, because otherwise this would have been a non-strict inequality according to the order of divisors. And so this means that VQ of A, sorry, VQ of X is strictly larger than 0. Right, because if you put kind of a Q here, then VQ of X is always larger or equal than minus VQ of A, but it's larger than 0. I mean, without the minus, it's smaller than 0, and after the minus, it's larger than 0. So this means that your function that comes from K has a 0. Right, there is a Q that X has a 0 at the point Q. And what constant has a 0 somewhere? Only the 0 constant. Right? I mean, you can't take 5 and it has a 0 somewhere. It doesn't have zeros. So this means that X is 0. I mean, coupled with that, I mean, this means that X is 0. Because the only constant that has a 0 is 0. Questions? Okay. You see, the definitions are kind of correct. You know, they abstract what you have in mind, I think, when you think about zeros and poles of functions and so forth. I'm not going to use the purple again. Okay. So here is another claim, but I'll leave it as an exercise because it's kind of the same. It's actually even easier. It's like a one-line proof. And you should do it yourself. The proof is also here. Okay, so actually it kind of follows from here. What can you say about N of 0? So here I took a strictly smaller divisor. I only required and gave you nothing back. Here I'm not requiring anything, but I'm not giving you anything. Actually, the proof, the answer is, the proof is here, but right. So it has to be the case that X is in K. Every element there is in K. Because K indeed have no zeros and no poles. So they fit there. And no other function fits there because it has a pole somewhere. So actually the proof is from there. Okay, that's an important space to understand. Like, yeah. Okay, good. And it's all heavily based on this fact that you will prove, I think, today, right? Oh, yeah. So that's, I don't think it's that trivial. I don't know. You will talk about it, but I mean, you know, depending on what you assume, but right. Here we only use the, it has a pole, I think. X has no poles. I think we used it here. So we use the fact that every element that is F and not in K has a pole. I think we use that, and maybe that we didn't. Sure. Right, it followed by taking X inverse anyhow. Yeah, someone said that. So here is another claim that is kind of obvious, but it's just playing with definitions. So I also leave it to you. Again, the proofs are here. I'm not leaving it to you like, you know, you can always look at there. So let's say you can take two divisors, but this is really just about definitions. And you take a subset of the prime divisors, places. Then what I'm claiming is that, kind of mix and match a little bit. Putting random letters on the. No, what I'm claiming is this. I'm claiming that, you know, here you have all functions that kind of obey A. Like, they have the 0 requirement and they use the pole allowances from A without any, you know, reference to S. Completely all of A. I think they should be a divisors. Okay, not pseudo divisors. They're finite. Okay, divisors. And here you have those from B, and you know this is bigger because B is larger, and larger is better, right? So like the positives are more positives, you get a lot of more poles, and the negative are less negative, so you have less requirement of zeros. So bigger divisors yields bigger Riemann-Roch spaces. And what I'm claiming is that you can really know, you can understand the. Oh yeah, no, sorry, right, sorry. So let S. Sorry, because S has to be somehow related to things, be the support of A and like the union of supports. Sorry. Good. I mean, I'm looking at all the. So these are divisors, I'm assuming these are divisors. So there is a finitely many prime divisors appearing here and finitely many here. I take the reunion and take it to be S. Note that it's not the same as saying the support of A plus B, because there could be cancellations. So I'm taking the union. And what I'm claiming is that how much bigger is LB from LA? It's exactly those elements here that you need to introduce. So these are all the elements in the truncated version of A. And this contains information about both A and B, so it kind of makes sense. It's really just a proof by, you just, use the definition and use the only step available next time. And you do it 5 times and you get to the proof, okay? In one direction. In the other direction, it's easier. In the one direction is obvious. This is contained in that, and this is contained in that. So in the intersection, but to prove this, you need to just, okay, yeah. Yes.
Within LA, S. No, but LB is not the same as LB, S. Why S is the spot? Because in LB you have constraints outside the.
Right. Yeah, the zeros are important.
Yeah.
Good.
So LB takes care of the
outside. Right. Exactly, and that's exactly how the proof goes, by the way. Yeah, good. But that's a very good miss that I also had just now. Good. Okay, so I'm just going to use that. I mean, some things you can prove everything, so that's an easy one that I'll skip. And here is another reminder before the next theorem is coming. It has nothing to do with our stuff. It has to do with vector spaces. I'm just reminding you, I think it's like the second, third isomorphism theorem. I don't remember the numbering. So if you have two K vector spaces, then there is this diagram. You can look at U, let's call it V, U, V intersection U, and V plus U. Right, the subspace generated by these two. And you do these things. And what I'm claiming is that the dimension of this over that is the same as the dimension of this over that. So the dimension, it's something that you know, but maybe you forgot, so I don't want it to appear in the middle of everything. You can put any one of them. Third or second, I don't remember. I think third has like double quotients. So maybe that's the second. And the fourth is the kernel image, I think. So it should be the second. I hope there is a fourth. Oh. Someone once said by the fourth, when I looked it up, and yeah, there is a fourth, but it's like not interesting. Like the dark triangle inequality. Don't you know? Yeah. So later, yeah. It's weird. It's like A minus B. No, I'll never be able to do that. It's like something like this or whatever. I'm not sure. Something like, who cared? So I'm going to erase that because that's probably not the right one. Okay, so why am I telling you this and that? Because now we are ready to prove something that is almost interesting. Like before Riemann's theorem, we are going to prove something very interesting. But this thing is, it might not look like it, but it's a very big step toward it. So what I want to do is to stop looking at these S's. I mean, write this theorem, or whatever it was, I don't remember how we called it, told you that we completely understand the dimension of these two, but only when you truncate to S, and you can truncate to S. It's like you don't have this in real life, you can truncate. It affects B and A. So you really want to understand the dimension of LB compared to LA without any reference to S. And with respect to the degrees. I mean, the degree is how much you allow, and the dimension is how much you get back, given that. The degree is how much is, is actually an amortized sum between how much you allow and how much you require. Pluses and minuses appear there, with the corresponding degree of the prime divisors. And the dimension is how many functions obey this. So you would want to say something like, if this is big, like if the degree is big, I'm allowing much more than I require, then the dimension also kind of gets big. Like in polynomials, right? You add one more here, you get one new polynomial. So you'd want that generally. There is an abstraction in our case when you don't talk about the rational function field because there are algebraic relations. So sometimes you allow something which may look like you actually allowed something new, but it was actually implied by the algebraic relations. So the questions about how does the dimension follow the degree is really interesting. And that's this lemma. It's the beginning of that. So if for divisors, only divisors, not pseudo divisors, we have, at the very least, you have the following. Kind of disappointing because, inequality is, I don't understand it. I just know it's not that much or whatever. And here you have like equality. So you can't compare the two technically, but that's going to be much more interesting. Okay? Yes. Yes. Here? Yeah, nowhere. I think nowhere. Right. That's just true. I mean, right. Yes. Yeah, I think maybe I just don't care about it. That's why I didn't. I mean, I don't remember why I don't care about it, but probably we just don't care about it. I think maybe you can add this. Right. I mean, we defined them, but we didn't call them Riemann-Roch spaces. So, but let's call them Riemann-Roch spaces, not telling like the old people that invented the field, and then you're right. I think it's fine. I'm trying to kind of get away from pseudo divisor, so maybe like unintentionally that happened. For During who wrote these notes, by the way. I mean, Dan Aran follows, I think, During's like old book. It's a typeset like with like a you see his handwriting. And it's like a very small book, but you see, it's like we're in page 10 or something. It's like very, very dense. Okay, so let's see the proof. Okay, so we have this thing, the truncated version we completely understand. Actually, the proof is by picture. You'll see it's very easy, given that. Because, I mean, you are allowing yourself some slackness, so you might expect it's easier. So you take the, as before, we take the support, the union of supports, of A and B, and it's finite because these are prime divisors. So you can use this lemma that appears there and what you know that the dimension, I mean, I'm just copying that really. And actually, the little kind of omission that we did together might say, well, if S is the common support, so maybe you should just remove the S everywhere because it doesn't affect the degrees really, right? Only the dimensions. Like the degree of BS is the same as the degree of B because it has zeros outside anyhow. So the degrees are not affected, but these are affected. So this is true, but you can't just omit the S's and have an equality because something as a zero matter. Like if a prime divisor appear in B and not in A, and you can't have it the other way around because B is larger, then the fact that it appears here, with zero here is not that it doesn't appear at all. It appears there, it has a requirement. So that's the only thing you can say. You can't say, let's remove the S, S is common to everything, who cares? But now there is a little picture that will immediately imply this theorem, or lemma.
Because in S you require all the stuff for different.
Yes, and actually you'll see it from here maybe even better because there is a picture that will tell you what's the difference. So here's the picture that I have in mind, and that will complete the proof. Let's look at the Riemann-Roch space of B, and that's actually a proper Riemann-Roch space, and this S-truncated version of the Riemann-Roch space of A. So we know that their intersection is what? I mean, it's hard, but it's a claim that we, right, so it's not completely easy, but that's that. And their sum is, it's whatever, it's their sum. I don't know what their sum is. But it is definitely contained in LBS. Because LB is here, because I just restricted even more. requirement. And this thing is here because B is larger or equal than A. And that's a subspace, so once it contains two subspaces, it contains the sum.
LBS is more constrained than LB.
Yes.
Less constrained.
Sorry, less constraint. Yeah, and that's why it's bigger. It's yes. I said that. And we know that this equals to that by this reminder that I talked about here. And so definitely, I mean, I want to prove, right? So, okay, we know that, I got confused. And we know that this equals to that. No, we know that this equals to the difference of degrees. Right, that's what we have here. This situation we completely understand. From here to here, the degree extension here is deg BS minus deg AS. But in degrees, the S doesn't matter. So it's really just deg B minus deg A. In dimensions, it does matter, but in degrees, it just S contains all the prime divisors. So outside is 0, so who cares about it in terms of degrees? So we know that this is the difference of degrees. It's definitely larger than that, right? Because, or equal maybe. And that's equal to this. So that's it. So this is smaller or equal than that. And you see, this is the difference. Like you ask, what happens when you lose S? So you get these functions that are here and not here. And so to really understand them, yeah, so it's like this claim. It's not the claim. The claim is about here, but you need to kind of figure out in your head, like, what benefit will I have from from looking at this compared to what functions I have here, which are not sums of functions from here. So you can do an exercise and kind of figure it out in like a rational function field just to see. But I won't do that. Okay, so good. So we proved that. And just as a corollary, that for some reason appears later in the note, so I'll put it right after. This one? Because of what I raised, the second homomorphism theorem. Like you have a U plus V, U, V, and U intersection V. Like generally speaking, this is the same as that, the dimension. Right. So it's like not tied to the Riemann-Roch space structure. It's a general fact, yeah. So just as a, so just to say it, so I don't know if I wrote to say it and now it's not appearing here. Yeah, here, it's a different. Okay, good. So, so as an obvious corollary, but it's an important corollary. Right, so this is indeed, I mean, when things are finite, and these are, oh. That's why it appears later. Yeah, good. Well thought. So what I wanted to say is that, this is indeed the difference of dimensions. So let me just say it and then just, I mean, it is the case. I mean, dimension of the quotient is the difference of dimensions given that they are finite, right? And that's why I put it later, or, during put it later. But let me just put it here. So from this lemma, we see that the dimension of LB minus the dimension of LA, which I'm not sure I introduced this notation, but this is we write it as dim-B. Instead of saying the dimension of the Riemann-Roch space of the divisor, we just say the dimension of the divisor is at most the degrees. I mean, assuming they're finite. Okay, assuming that both dimensions are finite. Which we will know in a second. So this is implied. So this means if you just shuffle things around, and right, I'm assuming that I'm always assuming that A is at most B as a divisor. So what really happens is that the degree of A, it should be right, but I want this to be larger. I just write what I want and it should be fine. Oh yeah, good. Thanks. That's okay. So yeah, that's true. Then that's also true. I mean, so what happens here is that if A is smaller or equal than B, and after Tomer fixed me and I wrote it correctly, So you see what happens is if you take the dimension back there and the degree here, namely you put the same divisor on each side and look at degree minus dimension, then you see that as the divisors increase, this difference, this deficiency increase as well, or at least doesn't decrease. And this thing is something important. This is what we talked about. Given this is the deficiency, like you allow or require whatever, this is given by that number, and this is how much you get for that. So this difference is how much you don't get, like how much you lose. This is the deficiency. You don't have examples of that because in the Riemann-Roch space, in the Russian function space, this is always 0. If you allow degree R polynomials, you have R plus 1. It's always not 0. It's always minus 1 or 1, whatever. I'm not sure, but it's always the same. But you see what happens as you increase things, as you kind of go more regularly, not weirdly in the beginning, the deficiency can only increase. Okay? So it's maybe good initially, but then worse. That's what I'm saying. Okay, so after the break, we are like a slide away from talking about the genus and stuff like that. Like, no, not really, but we'll see. Okay. Okay, so see you after the break.